Well, hello there, everyone. Yeah, welcome to the third online day of cs203. Yeah, that's a good question. I promise you I will send you out the link tonight to the Discord. And you all can join. Basically, it's going to be a little less formal than the 202, 201 Discords. For office hours, you can just kind of join the main channel and ask me a question, and then we'll work on it. So I think that's how it'll probably work. All right, let's get started. Yeah, so has everyone looked at the homework coming up? I think we're gonna give until Friday for that, just because I know I haven't had office hours working, so you can take until Friday to get it done. I'll try to hold my regular office hours. I'll try to be in here by about 11. So, and then I'll stay some amount of time. Okay. Well, let's deal with some combinatorial stuff today and see if we can make any progress. So, this has nothing to do with combinatorics per se. This is just a general term about functions. But I'd like to define injectivity and maybe surjectivity at some point. Basically, injectivity is the same thing as one-to-one, if you've ever heard that term before. So a function is one-to-one if basically any f of x is unique. The way that they generally say it in book definitions is whenever f of x is equal to f of y, then x is equal to y. So, for instance, we can always say that like f of x is equal to, say, 3x plus 2 is injective, or one-to-one. And the reason for that is because if 3x plus 2 equals 3y plus 2, then what we can do here is you can cancel out the 2's, and then you can divide by 3, and then you get x equals y. So that is essentially the proof that 3x plus 2 is injective. Let's look at an example of something that's not injective. So if you have f of x equal to x squared, then this is not an injective function, because if x squared is equal to y squared, then we can do a little bit of algebrating. We can subtract the y squared and set that equal to 0. And then what we can do is factor using a difference of squares. Now the problem with this factorization is that we see that x minus y times x plus y is the factorization. So that means that either x is equal to y and we would be happy, but here's the other condition. X can also equal to minus y, which means that x is not equal to y, at least when they're not equal to 0. So the point is that this function is not injective. But of course, like the better way to see it is just to say, oh, well, 5 squared is 25, and minus 5 squared is 25. So they have two x coordinates, two elements of the domain. So two elements of the domain that map to the same element in the range. And so this is why you would say that this function is injective, this function is not injective. Okay, so basically a function is injective when it's one-to-one. So the real question in combinatorics is, how many functions are there? So how many functions are there from a set of 3 elements to a set of 5 elements? And so right now we don't care. Injective will come into the next problem. So how many functions are there? So the first question is, what is a function? And so the answer is, basically, if you have a function which maps from a domain into a range, what that means is that f of x is a well-defined, is a single element of the range for all x in the domain. So what that really means is that basically the one thing that functions rule out is a function. You cannot have something like this: f of 3 is equal to 5 and f of 3 is equal to 2, right? So in this case, you might want to say something like f of 3 is equal to the set 2, 5. But we generally exclude this multi-valued functions. Let me just rewrite that. So functions that have their values in sets are generally excluded, as long as, or functions whose values are sets are kind of excluded for the most part. So basically the thing is that for a function from a set of 3 elements, so basically we want to know how many ways we can pick a to get assigned into a set of 5 elements. Let's say 1, 2, 3, 4, 5, right? So basically the rule is that a can be assigned to 1, 2, 3, 4, or 5. B can be assigned to 1, 2, 3, 4, or 5, etc. And C can be assigned to 1, 2, 3, 4, and 5. All right. So what can we do with this, right? So the answer is, in this case, each one of these has a choice. Each one of the elements of the domain has a choice of how many of which element it's going to go to in the range. And since it's just a function, it doesn't have to be a distinct element. It can be the same element, right? Because f of a can be 2, f of b can be 2, and f of c can be 2. That's okay. That doesn't break the fact that we have a function, because, for instance, f of x is just the constant. Function 2 is essentially the same thing as what we've just written down here. So, and that's a legal function in most of algebra. So basically we have 3 slots. We have the A slot, the B slot, and the C slot, and we have how many choices in each slot to determine where everything goes. So the answer is, it's really the range. So we have 5, we have 5, and we have 5. So therefore, there are 125 functions from a set of 3 elements to a set of 5 elements. Okay. Well, now the question is, how many injective functions are there? So how many one-to-one functions are there? And so in this case, instead of making, so how is this different than this question? The question is different because once A gets something that it mapped to, say A maps to 3, that means that 3 is off the list. So that means we can't pick 3 for B or C. Now, it wouldn't break it to be a function. Obviously, we could assign A to 3, B to 3, C to 3. That's a function. But then it would no longer be injective. It would no longer be one-to-one because we would have 2 elements that are mapping to the same element. So in that case, we'll draw our 3 slots up here. And then we'll say, the first, for A, we have 5 choices. For B, we have 4 choices. And for C, we have 3 choices. So as it turns out, this is actually the same as P5, 3. All right. So let's move on to the general case. So how many functions are there in a set of from a set of m elements to a set of n elements? Well, so basically the point is where m is less than or equal to n. So that's really more for this part of the question. This part, it doesn't matter. So I think the way to think about it is that we have to generalize this, right? So we have to generalize what's going on here. So basically here, the thing that we were multiplying together was the size of the range. So basically we have a set of m elements that's mapping to a set of n elements. And given that, what we're going to do is we know that each one of these is going to be the size of the set n, which is just little n, and it's going to, how many of these are there? There's going to be m of them, so it's going to be n to the power m functions. Basically, because what we're going to do is draw out m slots, and each one of them is going to have an n in it. And then the last question, how many injective functions are there from a set of m elements to a set of n elements? Now it's important that m is less than or equal to n. Here it didn't matter. This answer is defined whether or not m is bigger or less than n. But it needs to be less than or equal to n in this case, because what we're going to do is we're basically going to just say it's the permutation of n comma m. And so why do we need m is less than or equal to n for this to be defined? The answer is because if you remember the definition of it, Pn comma m is equal to n factorial over n minus m factorial. And so there is a kind of question, what is, say, minus 2 factorial? The answer is, who knows? Let's just define it to be 0 in this case. But let's just define these things to be 0 when m is bigger than n. We're not really assuming that being an injective function is correlated to permutations, but we kind of derived it because we notice here that if we have, say, let's say m slots, and we have n choices here, then the first choice is going to be n, not n minus 1, it's just going to be regular n. Then it'll be n minus 1, n minus 2, n minus 3, all the way down to n minus, I guess, is it m plus 1? Yes. So that's kind of the reason that we get a permutation out, is because when we do kind of the standard multiplication arguments, we see that a permutation ends up being the answer to the question. It's not guaranteed that it'll be, but in this case it is. The reason why it's a permutation and not a combination is because order matters in this case. If you have x0 and here's x1 and here's x2, x3, all the way up to x, I guess, m minus 1. I should have just made it x1 to xm. We see that the thing that gets assigned to x0 matters, and there's n choices for that. If we make a different choice, then there's going to be a different thing assigned to x0. So that's why we can't just say order doesn't matter. Otherwise, we're just saying that some element is assigned to whatever this thing was, and some other element is assigned to whatever that is. But then it's not really a function anymore because we don't have elements. We don't have exactly, f of x0 is equal to, say, y0, etc. Stuff like this. So, okay. So I just wanted to define the term injective. I think what I'll probably do, I might make a homework problem about it, but I might not even make it about combinatorics at all, in the sense that there's a lot of questions about injective functions. This is not online, but I can share it later. Okay, let's move on from this. Something a little bit, maybe just uncluttered. Okay, so this is just a combination problem. The turn-in thingy for homework 5 is probably not up yet, because I have probably forgotten to put it up. But I'll put that up tonight, or I'll put it up right after class, if I am reminded. So, I'm going to tell you that this is a combination problem. And so, let's just read the problem. A student council consists of 3 freshmen, 4 sophomores, 4 juniors, and 5 seniors. How many committees of 8 of the council contain at least one member from each class? Okay. So, it's not always obvious whether something's a permutation or a combination. The key word here, and remember the difference between permutations and combinations. The primary difference is, does order matter? So really what it is, it's even more annoying than that. It's actually because of the word committees. And so when you see the word committees, you think about egalitarianism. And so what I mean by that is that everybody on a committee is equal. And because everyone on a committee is equal, the order that we pick, so we're talking about the order of choosing, right? So the thing is that because everybody on a committee is equal, the person who's listed first on the committee, right, is all the way down to the 8th person. They're all the same. Like if I randomly permuted the order of the people on the committee, it wouldn't matter. It's just kind of like if you know, on a list of, say, people who've passed an exam, like it doesn't matter if you're number 1 or it doesn't matter if you're number 8, maybe you're even listed alphabetically. The whole point is like everybody on that list is on the team or passed the thing. Yes, we are talking about the order in which we choose. So the order of okay. So committees tells us this. If I was saying that we pick like one person to be president, one person to be vice president, one person to be treasurer, then different positions are non-equal. But committees are equal. Okay, so how do we do this kind of problem? It's actually a little complex. So here it says a student council consists of how many? 3 freshmen, 4 sophomores, 4 juniors, and 5 seniors. How many committees consist of 8 members of the council contain at least one member from each class? So basically, what we have to do is pick, what should I say? We have to pick a certain number of people from a certain set of these things. So we're going to pick 8 total. And so we need at least one member from each one of the classes. And so the number of ways to do this is you can either pick, say, 1 freshman, or 2 freshmen, or 3 freshmen. If you pick 1 freshman, then you need to pick 7 others. If you pick 2 freshmen, then you need to pick 6 others. And if you pick 3 freshmen, you need to pick 5 others. And so the point about this is that actually I think the easiest way to do this is to use the complement method. Because adding up all the different ways to do this would be huge in general. So we're going to ask how many ways can we exclude at least one class? So basically we're guaranteed right. No, we were not going to use the combinatorial method. What we're going to do is use or we're not going to use the complementary method. I think the simplest way to do this is the stars and bars method. And so, yes. What we really need is we need freshmen plus, say, sophomores plus juniors plus, I don't know, let's call it seniors, so say E, has to be equal to 8. And what we know is that 1 is less than or equal to F is less than or equal to 3. 1 is less than or equal to S is less than or equal to 4. 1 is less than or equal to J is less than or equal to 4. And 1 is less than or equal to E is less than or equal to 5. And so in order to do this general stars and bars method, there's a formula that you need to know. And basically what it is to pick, let's say, K groups out of N people. We can do this in N plus K minus 1. Choose N, or actually choose K minus 1 ways. And the reason for this is because if we have N people, say we have person 1, 2, 3, 4, 5, all the way up to N. What we get to do is, if we want to break this into K groups, what we're going to have to do is we have to choose, basically, yes it is. So we have to choose places for special bars to go. So for instance here, if we put 1 and 2 into a group, and then we say put 3, 4, 5 into a group, and then we put some other set of people, then the answer is actually that there were let's just think about this for a second before I say something. So there are quite a number of people. So how many groups are we picking? So we're picking K groups out of N objects. And so the answer is here that it's kind of the question is how many ways can we arrange if these were just replaced with stars and these are replaced with bars, and that's why I call it stars and bars. For instance, it's the number of ways that you can arrange K minus 1 bars. And so the answer here is going to be, well, so in this case, we know that f has to be at least 1. So what I'm going to, unfortunately, this problem, I accidentally chose it. It's a little too complicated for a first example of this. The way to really think about this is that we want to divide all these people into a certain number of groups. Yeah, so let's think about it for a second. If you have 3 plus 4 plus 4 plus 5, so how much is 3 plus 4 plus 4 plus 5? That's equal to 8, 11, 16. And so, and then we just want to split it into 4 groups. So yeah, I think there are 19 choose, basically 3, or 19 choose 16 ways to do at least part of this. The true answer is that we have to, there's a lot more work that had to be done here. I think I picked a problem that is too complicated. So I think what we're going to have to do is come back to this. I'm sorry, guys. This I think will be towards maybe the end of maybe the next class, because there's unfortunately just too much work in here. We will go over the stars and bars method again. It's important, but unfortunately, I think when I realize now that this is the solution to this, I'm like, oh god, there's just too much to do, and I have to teach the generalized inclusion-exclusion principle as well. So, yeah, let's move on from this one. Let's pick a problem we can actually solve. Okay, this is a good one. I know this one. So, well, I knew that one too, unfortunately, which is why I was like, oh god, we can't finish that one. So, yeah, I had a different idea about how to solve that one. Yeah, this is all in chapter 9, right? We're all still in chapter 9. It's all in chapter 9.3 and 4 in permutations and combinations. So, okay, here's a way shorter problem that we don't need. The only problem with the previous problem is that we needed like 2 or 3 things that I haven't said yet. So I was going to have to really go crazy. And I just wanted to not do that. So instead of that, let's just do a problem like this. So every morning a man walks 8 blocks to his office, which is located 5 blocks east and 3 blocks north of his house. So assume that the blocks are all rectangular, there's no blind streets, whatever that means. So find the number of different paths he may follow if and only if he only walks to the north and east. So let's draw the situation out. I think so I copied this problem out of a book. I think blind streets might be streets with no exit. So, but there we go, fixed. Okay, so here's home, and here's the office. And so basically here are possible paths that we can take. We can go like this. Or we could go like this. Or we could go like that. So let's translate all of these possible paths into a bunch of directions. So either you're going to go north or you're going to go east. So for this path, this is an east, then north, north, east, That's obviously north, so that cannot be east. Okay. So let's look at this word here that we make. We make an EN, ENN, EN, E, E, E. Let's look at the red path. What do we make with the red path? What we make with the red path is an N, N, E, N. Then we get 4 E's. And finally, with the blue path, we're going to get N, E, and then I think a bunch more E's, and then finally 2 N's. So, what describes all that? Like, look at these. So look at these words and tell me the thing that you know how to do with words like these, right? So we learned previously about distinguishable permutations, right? Ah, crap. Okay. And so how do we know? So basically what we have here are words that are 3 N's and 5 E's. And that's what we know about them. So the real question, this problem becomes equivalent to how many distinguishable permutations are there of these 3 words, or of any of these words? And the answer is 8 factorial divided by 3 factorial, 5 factorial, right? Because you just take the total factorial divided by each number of repetitions factorial. The reason why this also can be a combination problem is because, as it turns out, this is 8 choose 3, or alternatively 8 choose 5. Okay. I don't know what you mean. Why do I multiply on the bottom? Sorry. Okay. Anyway, so yeah, if you just explain yourself a little bit, I'll answer that question. Otherwise, yeah. So any other questions about this one? So this one is a good problem because it shows you how. Oh, so the thing is, remember that what we're doing here is it's 8 factorial is the number of ways, is the number of permutations of 8 different things. And then what we have to do is divide by the number of, 5 factorial, which is the number of permutations of 5 things, because all of the E's are the same. And then we have to divide also by 3 factorial. So it's because we're doing, because both the N's are indistinguishable, and yes, so this is, you can either consider this a distinguishable permutations problem, or you consider this a combinations problem. Because as I say, as it turns out, when you're doing distinguishable permutations of 2 things, it is always going to be equal to a combination as well. Yes, this is exactly like that. Okay. Cool. All right, so I think I'm going to move on. Cool. So here's a question that, again, doesn't require stars and bars, thank God. In how many ways can a group of 6 boys and 6 girls be divided into 2 equal groups, so that each group contains an odd number of boys and girls? So basically, if we're going to divide two groups of people, so we have 12 people total, and we're going to divide them into two equal groups, right? So the answer is that each group is going to obviously have to have 6 people, right? So I guess what we mean by equal here is equal in terms of just the total number of people. We don't mean equal in terms of genders. So we want each group to contain an odd number of boys and an odd number. Well, I guess if it's going to contain an odd number of boys, then it's automatically going to contain an odd number of girls. This is an odd way to state a problem, but I just stole this problem directly. But the point is that so when you're looking at a problem like this, what are the options for odd numbers here? Yeah, exactly. So either there's 1, 3, or 5, let's just say boys. But of course, if there's 1 boy, then there's 5 girls. If there's 3 boys, there's 3 girls. And if there's 5 boys, then there's 1 girl. Right? So it really doesn't matter which one you consider to be like the thing that we're actually going to loop through. Okay, so basically, the number of ways to do this is equal to this. So either out of the 6 boys, you pick 1. And if you pick 1 out of the 6 boys, then also we have to pick 5 girls. So we're going to, out of the 6 girls, we pick 5. So this is one way to do this. Or I'm sorry, this isn't one way to do this. This is the number of ways we can do it such that we pick 1 of the 6 boys and 5 of the 6 girls. Here is another term. You pick out of the 6 boys, you pick 3. Out of the 6 girls, you pick 3. And so this is the number of ways to pick evenly. And then here's the symmetric term. So either when you pick 5 boys, then you have to pick 1 girl. Okay. So yeah, so here's the way to think about it. It's the question is whether or not you use, is it an and conjunction, which is multiplication, or is it or, which is addition? If it's or, then you need to add. If it's and, you need to multiply. So when you're picking a group of 6 people, first you're going to pick 1 boy and 5 girls. Or you're going to pick 3 boys and 3 girls. Or you're going to pick 5 boys and 1 girl. And that's, so, I mean, literally you can just have a function that, f of and is equal to times f of plus. Oh, I'm sorry. Excuse me. Couldn't mute it in time. All right. I know what all of you guys are going to say. You're going to say, it's the corona. Thank you, everybody. Okay. So I think so let me just say, what are decent test questions? This one here about the paths, it's a good question. Here's another good question, right? Because with enough practice, you can kind of, keep just drawing straight through everything. With enough practice, you can definitely do this stuff. Let's say that this stuff is not the stars and bars stuff. We'll leave that off for now. All right, let's look at another problem. Okay. Do we want to do this one? Yeah, why not? So, okay. So this is not such a bad question. What we're going to do for this question is a combinatorial argument. And all of you are thinking, oh, what is that? That's what he said to do on the homework. So we're not going to do this using... So you see this horrible formula. What we are not going to do is prove it using a huge amount of algebra. No algebra. We're going to say words. And those words are going to convince you that it's true. So let's talk about the Bell numbers. So these are the Bell numbers. And so what we're going to do is imagine I have the numbers 1, 2, 3, 4. Yeah, let's just start with 4. And I ask, how many ways can I put these into different boxes? So one way to do it is to put them all into the same box. Another way to do it is to put 1 into a box, 2, 3, 4. Or I can put 2 into a box, 1, 3, 4. Or I can put 3 into a box, 1, 2, 4. Or I can put 4 into a box. And then we have 1, 2, 3. And then I can also do a bunch of other stuff. I can say pick 2 elements, 1, 2, and then 3, 4 are left. I can pick 1, 3, 2, 4 are left. I can also do something like this, where I say, I'm going to pick 1, 2, put that in a box, but I'm also going to put 3 in its own box, and I'm going to put 4 in its own box. So, and there's lots more of these, right? I can always say, put 2, 3 in a box, put 1 in a box, put 4 in its own box. So the question is how many ways I can divide up elements such that they are in their own boxes. Or not in their own boxes, but just in boxes of groups. So yeah, so let's look at that equation and ask, what does it mean? So if we look at this, basically we're going to say that the number of ways to divide things up into boxes, yeah, there's no constraint. So the final thing here is going to be everything is in its own box. And then there's other combinations. So the only rule is that every box that you create has to have something in it. So if you have an empty box, it's the same as not having one. So these are called partitions. And you see here is a partition where I've put 1, 2 into a box, I put 3, 4 into a box, and I put 5 into a box. I could also have the partition that's just 1, 2, 3, 4, and 5 all in the same set. I can also have, 1, 3, 5, 2, 4, like that. There's a lot of partitions. So the question is how many ways can we count them? And so let me try to make an argument. This argument is all going to be words. There's not going to be a whole lot of algebra. And so the argument is basically this. How many ways can I put n objects? So this is n objects. Into boxes. Well, here's my argument. What you can do is you can take... Well, okay, so I think the way to start is you say, list the elements 1, 2, 3, all the way up to n. And then what I'm going to do here is I'm going to say, okay, 1 is going to go into a box, but I don't know if there's more elements in here or not. What I'm going to do here, n minus 1 choose 0. That means out of the rest of the objects, I'm going to pick none of them. So 1 is going to get its own box this time. And then I'm going to multiply by the number of ways to put things in, right? So we want to box up n minus 1 things. Or what we can do is we can pick... Actually, I think this should probably be a 1 here. Or am I wrong? Oh, I'm sorry. That shouldn't be 1. That needs to be a 1. Okay, cool. So what we're going to do is then we're going to take 1 and put it into a box. And what this says to do here is pick one other thing. Say we pick 5, but it can be anything. So the number of ways to pick one thing out of n minus 1 things is n minus 1 choose 1. Well, this is not exactly a permutation or a combination. This is like a sum of different... It's like a sum of combinations that isn't exactly anything. But then if I've boxed up 2 things in here, then we have to box up n minus 2 things left. And then for the next term, it's going to be an n minus 1 choose 2 times b n minus 3, which will then say, okay, put 1 in a box, put 2 other things in with it, plus 2 other things, and then box up the n minus 3 things. And so we continue in this fashion all the way down until what this thing says, what this last one says, is put everything into the box with 1. So we put 1 into the box, and we stick the rest of the stuff in. And then we have to box up nothing. So there's no more elements. So here is the argument. So either we put one thing by itself and then we box up the rest, or we put 2 things in a box and we box up the rest, or we put 2 things and then here we put 3 things in a box and we box up the rest. We put 4 things in a box and we box up the rest, all the way down to we put everything in the same box and then there's nothing left. So as it turns out, that is the same as this formula here, right? We pick nothing to go into the box with 1, we box up everything else. We pick one thing, sorry about that. We pick one thing to go into the box with 1, and then we box up the rest. We pick 2 things to go into the box with 1, and then we box up the rest of the stuff. That would be a bn minus 3, all the way down until we pick everything to go into the box, and nothing is left. And so that's the proof. That's a combinatorial argument. Yeah, as it turns out, bn minus 1 is a part of bn. Yes. Because I would say it's mostly words. You can replace all the plus signs with algebra. So basically that's what I mean by combinatorial argument. And I will show you some more combinatorial arguments in the next few minutes. So yeah, this is a pretty good one. Okay. That is the proof. The proof is that you pick a number of things to go into the box with 1, and then you have to box up the rest. And you can either do that with no extra elements, 1 extra element, 2 extra elements, all the way down to all the elements. And that is exactly what... Okay, let me try this again. Okay. No. So how many ways to box n things? Let's just do this argument all over again. Let's do it. So either okay, so first I guess what I should say is put 1 in a box. Okay, then the next step is either we pick no extra elements, so if you pick no extra elements to go into the box with 1, then that means that we have to box up n minus 1 things separately. Or we pick 1 extra thing to go with 1. But if we are proving something. We're proving that formula. So if you pick 1 extra thing to go with 1, then that means you need to box up n minus 2 things. Or you pick 2 things. Which means you have to box up n minus 3 things. And then you continue down the road until you say, or you basically pick everything. And put it with 1. And in that case, so the smallest number of boxes is 1, because that would be that everything is in the same box, and the largest number of boxes is n, where everything is its own box. Yep. And so basically here now we just have to ask, so the number of ways to box n things is called Bn. And so either we pick one extra element. So out of the n minus 1 elements, we pick 1. And then we box up n minus 1 things, b n minus 1. Or we pick, I'm sorry, no extra things. There we go. Or we pick one extra thing, which is n minus 1, choose 1. And then we box up n minus 2 things, b n minus 2. Or we pick two extra elements, n minus 2. n minus 1, choose 2. Times the boxing up of n minus 3 things. And finally here, this would be, we pick everything, and then we don't have anything left to box up. So, once you do all that, you see all these either-ors, and you know that in combinatorics, or usually just means add. So in this case, the reason why I say usually is that these events all have to be distinct. So assuming there's two boxes. So what we're doing here is we're asking how many things go with 1, right? Either nothing else goes with 1, or one element goes with 1, or 2 elements goes with 1, or 3 elements, or 4 elements, all the way down to all the elements go with 1. And so what we're doing is then we're saying, well, I don't know how many ways to box up the remaining stuff, but I'll just multiply it by that number. And so you see that that's the formula that we get on the previous page. So this is a hard combinatorial argument, but I'm glad that we went through it, actually. It was a little bit terrifying, I think, but it wasn't bad. How many different ways can we box n things with up to n boxes is the answer. Yes. One has to go into at least one of the boxes. Okay. So, let's see here. Okay, let's prove this. I'm going to show you an example where we prove something. Let's prove this by induction. Yeah, so the thing about it is, induction, as I always say, is where you don't really understand what you're proving. And if you look at this formula, you might think to yourself, I don't really understand what this formula is saying. So let's prove it by induction. So what's the base case? So the base case is going to be, so m, you notice here, m is just fixed. But it's kind of arbitrary. So we're going to have to induct on n. So what's the base case? So the base case is when you set n equal to 0. So then what we're going to end up with on this side is the sum from k equals 0 to 0 of m plus k, choose k. So what exactly is that? So that's equal to and so m plus 0 choose 0 is actually m choose 0, which is just, well, let's write it out. So it's m factorial over 0 factorial times m minus 0 quantity factorial. right? Oh, this is excellent, because now we get practice. So, what is m factorial? Well, who knows? But we're dividing by another m factorial here, right? What is 0 factorial? I haven't even looked over there yet. I haven't checked on that. So 0 factorial is 1. So these two things cancel and give us a 1. And so this whole term is just 1. All right, now let's look at this side. So if we do m, and remember that n is equal to 0 because we're still in the base case, 0 plus 1, choose n, which is again 0. And so now this is m plus 1 choose 0, but the good news about m plus 1 choose 0 is that you know that it didn't really matter that this was m choose 0. Anything choose 0 is just going to be 1. So therefore these two things are equal. Cool. So that's the base case. So now let's assume that the sum of m choose k, or m plus k choose k, is equal to choose n. All right, so now what? So now what we're going to do is we want to look at this thing. And what we know is that this thing can be broken down. So we know that basically this thing is equal to the sum from k equals 0 to n of m plus k choose k plus one term on the outside. So we've split the n plus 1 term off. And so what that's going to be is it's going to be, remember we're plugging in that for k, so it's going to be plus m plus n plus 1 choose n plus 1. Awesome. So, what should we do to this thing? What's the only thing you can do in an induction proof? Yeah, we apply the induction hypothesis, right? So what does the induction hypothesis say about this thing? Well, this thing is the horrible sum that we don't understand, right? But the good news is that we've assumed that it's equal to this other term here. So we got the m plus n plus 1 choose n plus 1 from this summation because the thing is that when you sum up to n, it's going to give us all the terms that we had in the previous one. When you sum up to n plus 1, it's going to give you all of that, which is all of this, plus whatever happens when you plug in n plus 1 in for k. Right? So you got to substitute in n plus 1 into both of those k's. And then you can split it off from the sum. It's basically like saying the sum of n from 1 to 5 is equal to the sum of from 1 to 4 of n plus the last term. Okay, so I'm going to apply the inductive hypothesis here. And I'm just going to say that this thing is equal to m plus n plus 1. Choose n. And this is plus m plus n plus 1. Choose n plus 1. So I haven't actually I haven't plugged anything into the other side for the n plus 1. We've just started looking at this term. We've broken off this thing. You notice that this thing is actually not, this m plus n plus 1, choose n plus 1, is not exactly the same as this term. So here's a thing. This is actually your homework problem. So in your homework problem, I tell you to prove that if, say, n choose, well, let's just say a choose b plus a choose b minus 1, and that is going to be equal to a plus 1. Choose b. So because of that, we see that this m plus n plus 1 is a. We see that b is equal to n plus 1. And so what we're actually going to get here is m plus n plus 1. So a is equal to m plus n plus 1, and b is equal to n plus 1. And so what we're going to get here is that this thing is equal to m plus n plus 2. Choose n plus 1. So then we look at the original summation. We say, assuming this is true, well, when we plug in n plus 1 on this side, we get the formula for n plus 1 on this side. So we are done. So there are combinatorial arguments for this kind of thing. The combinatorial arguments are basically that if you're going to pick n things out of m plus n plus 1 things, it's the same thing as already having picked, say, a certain subset of them, and then kind of cycling up from 0 all the way up to n. So there is a combinatorial argument for this. So the original problem says that you want it to be m plus 1 over n, and so the thing is that if you substitute in n plus 1 here, what you're going to get is, on this side, you're going to get m plus n plus 2, choose n plus 1. And so that is the term that we wanted. Yeah, so this is a, maybe I'll write this one up. I think this one is good, but hard. All right. So we did the last one with induction, and induction is horrible. We're going to do this one with a combinatorial argument. Okay, so what are we going to do to prove that n choose k times k choose m is equal to n choose m times n minus m choose k minus m. So first thing is you want to look at each side of these things and just spend a time thinking about what it means. So first, right, I have a bag of n things, and I pick k. So then I have a bag. Then basically what I do is I throw them all into a new bag. So a new bag. And then out of those k things, I pick m. Okay. So if we think about this in this way, then what we're going to do is we're going to say, is that the same thing as choosing out of a bag of n things, pick m, then with the n minus m remaining, we pick k minus m. And the answer is going to be yes. And here is the argument why. Here's the argument why. So I have a bag of n things. So I'm going to break it up into a bag of n minus k things and a bag of k things, which I then break up into a bag of n minus k things, k minus m things, and m things. So this is right here, I'm just showing you what n choose k times k choose m is, right? You start with a bag of n things, you break it up into two other bags with n minus k and k things in it, right? This is like what's left over, and then you have the leftover bag, and then you pick another m things out of this other bag, so this becomes that. So now let's look at this, what happens when we do this. So if you have a bag of n things, we're going to get a bag of n minus m things, and we're going to get a bag of m things. So actually this bag of m things here matches with this one here. So now all we have to do is make sure that when we do this next selection, the thing matches. So let's see what happens when the thing matches. So what we're going to do now is we're going to say, out of these n minus m things, pick another k minus m things. So how do you do that? So if you pick out of n minus m minus k minus m things, then what we really have is n minus m minus k plus m things. So the m's cancel. And so when we do this selection, we're going to end up with a bag of n minus k things, a bag of, I guess technically it's going to be k minus m things. Ah, right. And then the bag of m things. So you see that in the end, this is two different ways to go through the selections that end up with the same set of things in bags. And so basically, that is the argument that you can use to prove that this is true. Now, if you wanted to use algebra, algebra works, as it turns out. So if you just write down what all of these things are, for instance, you say, okay, n factorial over k factorial, n minus k factorial, k factorial over, actually you don't even need induction, m factorial k minus m factorial, and you ask the question, is this equal to n factorial over m factorial n minus m factorial times n minus m factorial over k minus m factorial, and then the last term is going to be a what? It's going to be n minus k factorial. And so if you look at all of this, so the answer is you can kind of combine algebra and words. But here what you see is that you can actually cancel out these k factorials. And here you can cancel out these n minus m factorials. And once you do that, what you're going to see is that you have an n factorial on both sides. You have an m factorial in the denominator. You have a k minus m factorial, and you have an n minus k factorial. So as it turns out, you can prove this with algebra. And the proof of algebra is literally the proof here. It is a little like the ratio test, isn't it? As horrible as that is. So, yeah, so basically the point is that this is just a matching terms thing in algebra. But so what I'll say is this. When you think about things that are combinatorial, when you think about choosing things, this means choose k things out of an n-sized bag. This means choose m things out of a k-sized bag, etc. Sometimes you will get understanding from these formula proofs. But personally, I don't think that there's actually a lot of understanding that goes on in here. This is just symbol crunching. Down here, where you say, okay, I'm going to split things into 2 bags and then 3 bags, and then I split them this way into 2 bags and then 3 bags, and then I realize that by doing that, all the bags have the same size. So these 2 combinatorial expressions should be the same. Now, this is a decent combinatorial argument that actually I think gives you understanding. If you think about it, like this will actually give you understanding of what's going on, whereas this this algebraic argument will probably not. Okay. So maybe next time we'll do something way simpler next time. We're going to do inclusion exclusion next time. And I'm going to open up office hours on Discord tonight at some point. I'll send you guys an email with an invite. Okay. So, yep. I guess it's good that we didn't get to all of these questions. Some of them are more interesting than others. This one's a good one for just straight up algebrating. There's not really a good I don't know of a good combinatorial argument for this one. This one is a good proof by induction. So anyway, oh, I forgot what it's equal to. Okay, I think that's it for today. Sorry about the confusion on the first example problem. That was way too hard. I will definitely, we'll talk about that problem once we finish the inclusion-exclusion principle. Okay. I'll let you guys go. Have a good night. See you Wednesday.